Okay, so we're in section 1.2 now. We're looking at initial value problems. In the previous section, 1.1, when we talked about solutions to a differential equation, we saw that solutions tend to come in infinite families, n parameter families for an nth order differential equation. Those families of solutions are, as the name implies, given with parameters, usually denoted by the letter C, representing some unknown constant. And for any real number we put in for those C's, we create a new valid solution to the original differential equation. I mentioned back in section 1.1 that in applications, that's usually not enough. We're looking for one specific function that we can use as a model for some kind of physical phenomenon described by a differential equation. And solving that differential equation as is usually gives us that infinite family of functions. Our job now is to figure out how to narrow down that infinite family to one specific function that meets the criteria we're looking for. And in order for that to work, in order for us to be able to narrow it down in that way, we need more information than just the differential equation that we're given. Typically, what we need are something called initial values or initial conditions. So we're going to start with a description or a definition of what an initial value problem is. Specifically, an nth order initial value problem, IVP for short, initial value problem. An initial value problem has two components to it. It has a differential equation that we wish to solve. Now, this differential equation right here is given in normal form, but an IVP, an initial value problem, doesn't necessarily have to start with a differential equation in normal form. That's just the way it's represented here. And then we also have to have these additional things called initial values or initial conditions. And what these are, you can think of it as data almost. It's points that were, or ordered pairs, I should say, that have to satisfy the function and or its derivatives. So let me be a little bit more specific. Suppose we have an nth order differential equation here, and we're looking at a general IVP that uses this differential equation. We would be given this differential equation where the function here in this case is called y, and then we'd be given a set of values. X naught is going to be a common input that we use in all of these values here, and we look at the value that we get by plugging x naught into our function y, and we're given some output corresponding to that y naught, and then x naught plugged into y prime gives us a different value, y1, and we plug x naught into all of those derivatives up to the n minus 1th derivative. What this does is it gives us some points to work with, which we will then use to solve for the parameters that we need to get a specific function out of that infinite family. Right now, this is speaking in very general terms. It's going to become more concrete what we're talking about here when we get to the example at the bottom of this page. But to give you kind of a graphical illustration of what we're talking about, suppose we have some ODE, some differential equation, and suppose we've graphed several of its solution curves. So here's an example. This is straight from your book. Several solution curves for some differential equation that we're not actually given here. Each of these curves comes from a valid solution to that differential equation. But if we're also given a point, x naught, y naught, that is supposed to be on our curve, it looks from the ones that we've graphed, only one of those curves actually contains the point of interest here. So that single point that we're given, that initial value or initial condition, as we call it, helps us take this infinite family of solution curves and narrow it down to just one satisfying this additional criteria. Depending on the order of the differential equation, it may not be enough to only have one point. We may need more information about the correct solution curve. So for example, if it's a second order differential equation, then not only do we need some point x naught, y naught that's supposed to lie on that curve, but it turns out we also would need to know the slope of the that curve at that point. What is the value of y prime of x naught at that point there. And the reason for that is in a second order differential equation, you may have solution curves that intersect. And if several solution curves intersect at that point, then that means that point alone is not enough to narrow it down to just a single unique curve that we're looking for. So that additional information helps us narrow things down. Let's do an example to help make some of this a little more concrete. So we have an ODE here, y prime plus 2xy squared equals 0. And we're told that y equals 1 over x squared plus c, remember c is your parameter, is a family of solutions for this ODE. We're not asking you to verify that. We're just going to go ahead and accept that this is a family of solutions for this, although that would be easy enough to verify. Okay? Now it says determine a solution to this differential equation satisfying y of negative 2 equals 1/2. This is an initial condition. Okay, we're given an input and a corresponding output that would come with whatever the correct function is that we're looking for. And then it says give the largest interval I over which the solution is defined. Remember, solutions to differential equations come with these intervals of validity that we talk about. So there's a couple of things that we need to do here. Let's start with this. This initial condition, y of negative 2 equals 1/2, is giving us an input and an output that we can substitute into our family of solutions here. So in other words, my output 1/2, that goes into the y, 1/2, equals, I plug negative 2 in for my x squared here, 1 over negative 2 squared plus c, which is of course equal to 1 over 4 plus c. Okay? 1/2 equals 1 over 4 plus c. That's easy to solve. C in this case would equal negative 2. Okay? So what that means is that the function that satisfies not only this differential equation, but simultaneously this initial value, this initial condition, is the function from this family that I get from setting c equal to negative 2. So the function we're looking for is y equals 1 over x squared minus 2. All right? Now, the next thing it says is that we're to give the largest interval I over which this solution is defined. Now, this solution, if we don't think of it as a solution to a differential equation, if we just think of it as a normal function, the domain of this function is negative infinity to negative root 2 union negative root 2 union root 2 to infinity. And again, that's because the domain of this function is the set of all real numbers except for plus or minus root 2, which is easy to verify. Now that's the domain of this thing as a function. We don't get to use that entire domain if we want this to be considered a solution to that differential equation. Remember, solutions to differential equations should consist entirely of just one interval. And it's saying the largest interval I over which this solution is defined. We have some choices. We can pick any one of these three. And yes, these two intervals on the outside, root 2 infinity, negative to negative root 2, definitely intuitively would seem larger than this because they kind of stretch infinitely in one direction or the other. But kind of what we mean by the word largest here is we don't want to look at subintervals of these for I. So what an example of that would be something like this. An interval that can be considered a subinterval of this would be the interval, say, 10, 11, right? The set of all real numbers between 10 and 11 is contained entirely within this interval. So that would mean that interval could be an interval on which we define this function as a solution to our DE, but it's kind of small and there's no reason to restrict it that much. So we can select this entire interval and call that our interval of validity. So really the two largest choices for I would be this guy, negative infinity to negative root 2, or root 2 to infinity. So there's not a single correct answer to this. Either one of those is technically a valid choice. All right. Moving right along. Let's do a second order ODE for an example. So we're given the following ODE, x double prime minus x equals 0. And we're told that this is a family of solutions. X equals c1 e to the t plus c2 e to the negative t. I encourage you to verify. This one's very easy to verify. I encourage you to check that and make sure that it actually is a solution to this differential equation. I also want to point out something that we've already pointed out in 1.1, just want to reiterate that in the case of a second order differential equation, we end up with a two-parameter family of solutions. Again, the number of parameters here will generally match the order of the differential equation here. We're also asked to determine a solution to this differential equation satisfying x of 0 equals 0, x prime of 0 equals 0. Notice with the initial conditions this time, we're not just given a point on the curve like we were in the previous section. We're given two pieces of information. X of 0 equals 0, x prime of 0 equals 0. So again, associating that with the order of our differential equation here, a second order differential equation should have two data points, if we want to call them that, two initial conditions. And if it were a third order differential equation, we would have three initial values or initial conditions to work with. It'll always match the order of that differential equation. Okay, not only that, we're given points on the curve itself, and then we're given an x prime of that same input here, 0 and 0 in both cases. X prime of 0 equals something. If this were a higher order differential equation, we might have x double prime, x triple prime, so on and so forth, all the way up until the derivative that would come right before the order of that differential equation. So first derivative showing up here, second order differential equation. Okay, so same as before, we want to solve for the C1 and the C2 for those two parameters so that we can narrow this down to a single solution. And we do that by plugging values in. My independent variable here is t, and my output in this case is 0. So if I plug a 0 in for x, that's equal to C1 e to the 0 plus C2 e to the negative 0, which is the same thing as 0 equals C1 plus C2. And then I have x prime of 0 equals 0. So we need to find x prime first. X prime would equal C1 e to the t minus C2 e to the negative t. And I do the same thing. I plug a 0 in for x prime, since that's what the output's showing here, and 0 is also plugged in for t. So I get 0 equals C1 e to the 0 minus C2 e to the negative 0, which is the same thing as saying this. 0 equals C1 minus C2. Now here's why we needed those two initial conditions. Because each initial condition produced an equation where the parameters were my unknowns. And because I had two initial conditions to work with and two parameters to solve for, that gave me a system of two equations in two unknowns. So I solved this system of equations to wrap this example up. Let's add. This is going to give me 0 equals 2c1, which in other words means that c1 is equal to 0. In addition to that, if I were to substitute c1 equals 0 into either equation and solve for c2, I would also get c2 equals 0. Okay, so in this case, taking those two constants, c1 and c2, plugging them in for the parameters up here, I get x equals 0 plus 0, or just the constant function x equals 0. That's, remember, we call that the trivial solution. I can verify that this is in fact a solution by plugging it into my original differential equation and checking that it satisfies both initial conditions. If x equals 0 is the solution I'm working with, then x prime would equal 0 as well, because it's a constant function, as would x double prime. So these would both clearly be zeros. That satisfies those pretty easily. Also, this would look like 0 minus 0 equals 0, clearly true. So the answer here is the trivial solution, x equals 0. Okay? Let's look at another example. In this case, I'd like to show that this initial value problem over here, this IVP, has two solutions. dy dx equals x y to the 1/2 power, and my initial value here is y of 0 equals 0. I'd like to show that this has two solutions, these guys, okay? Starting with the first one, y equals 0 would imply that dy dx equals 0 as well. It's a constant function. Plugging that into both sides here, I do in fact get 0 equals x times y to the 1/2 power. Remember, y equals 0 as well, which of course is equal to 0. So that checks out. This constant function definitely satisfies both the differential equation and the initial value. I can see just without plugging anything in directly that the initial value is clearly satisfied here. Let's take a look, though, at the other function. So the other function is a little bit more interesting. We're given y equals 1/16 x to the 4th. Y equals 1/16 x to the 4th. That implies that y prime is equal to 1/4 x cubed. Okay? Now, I guess for consistency, I probably should have called it dy dx, but it's fine. You understand what that means. So if I plug this y prime in for dy dx and this y in for this y here, I want to show that both sides are equal to each other. So dy dx is equal to 1/4 x cubed. Is that equal to x times y to the 1/2? Well, again, y is this. 1/16 x to the 4th to the 1/2 power. Simplifying that down, I have x times 1/16 to the 1/2 power is 1/4. X to the 4th to the 1/2 power is x squared. And then multiplying the x times the x squared, I definitely get 1/4 x cubed, which is what I was hoping to get. Okay? Does this also satisfy the initial value? Well, again, I can do this by inspection. Plug in a 0, I should get a 0 out. If I plug a 0 in for x, y is clearly going to be a 0 as well. So both of these satisfy the same IVP. Now that presents a little bit of a problem, because again, if you think about why we care about these initial values in the first place, the entire point of that was to be able to take an infinite family of solutions to a differential equation and narrow it down to just a single solution from that family satisfying that initial value. But in this case, we got more than just a single solution. We got two solutions, and we were able to verify that. So that sort of raises a question. Clearly, an IVP does not always generate a unique solution, but we would like to know under which conditions it will do that, because that's what we really would like to have happen. We would like to have a unique solution to such a problem. So there's different theorems that surround this idea, and the one that we're going to talk about is going to be a little bit tricky to wrap your mind around, especially if you have not had calculus 3, because it involves partial derivatives and stuff like that. But we're gonna go through it, and we're going to do a couple of examples that utilize it. So we're talking about the plane, first of all, the xy coordinate axes and the Cartesian plane. Let's suppose that R is a rectangular region in the xy plane, and it's given by these two intervals. We'll give you a picture on the next page to illustrate this. So x is on the interval, the closed interval AB, y is in the interval, closed interval CD. And let's suppose that interior to that rectangle is some point x naught, y naught. This x naught, y naught is going to represent the initial condition. Okay, so keep that in mind. Now there's two functions that we're going to look at here, two multivariable functions, f of x, y, and the partial of f with respect to y. If both of these functions are continuous on that rectangular region R, then this is the consequence of those conditions. There would exist some interval that I'm going to call I naught. This interval is centered on this x naught right here, centered at this x naught. X naught minus h, x naught plus h, where h is some positive number. And this interval will be contained in the closed interval AB. Remember, AB, that closed interval, is basically defining the width of this rectangle R here. And there will also be a unique function y of x defined on that interval that is a solution to this IVP. Now this f of x, y up here, which seemed to come out of nowhere, is given down here. dy dx equals f of x, y. If you have a first order IVP, a first order differential equation, ordinary differential equation, and we know that this is a first order differential equation because dy dx is the highest derivative that we see showing up anywhere. There's no y double primes or anything like that. If you have a first order differential equation given in normal form, dy dx equals this, then the f of xy showing up here is the one that we're referencing here and here. Okay, so again, if you have this ODE in first order ODE in normal form, then this function f of xy would need to satisfy these two properties on that rectangle R for there to be a unique solution to this differential, IVP here. Okay, again,